All right, everyone. So today I'm going to be talking about Chapter 1, Section 1 of Sakurai. This chapter, or section rather, is about the Stern-Gerlach experiment, which was arguably one of the most important experiments in quantum history because it gave us sort of the first direct evidence for this purely mechanical or purely quantum mechanical property called spin. So before I actually dive into what the experiment was or how the apparatus was set up, I just want to note that the important thing about the Stern-Gerlach experiment was that it told us that the magnetic moment of an atom, and sort of by extension its angular momentum, is quantized. And so classically, you might expect that the magnetic moment might point in any direction, but this experiment ultimately showed that that wasn't true. It showed that it can only take on specific discrete values. So discrete and quantized meaning essentially the same thing, and just meaning that it's not continuous. And so we ultimately determined later that this property wasn't related to the electron's orbit and actually related to the inherent spin in an electron. And then, of course, it was eventually named the spin angular momentum. So now to get into a little bit about how the apparatus was actually set up. Right. So essentially, what Stern and Gerlach had set up was this furnace here with silver inside of it, and this furnace was getting super hot, and it was essentially vaporizing these silver atoms, and those silver atoms were being injected out of this furnace, right? But if you're just vaporizing these silver atoms, you can't force them to go in a straight line, right? So how do we make sure that they're in a straight line? The answer for that is you just block off all the ones that aren't in a straight line. Right, so this collimator here is essentially just a set of slits, right? And those slits just ensure that if an atom is coming out that's not in a perfectly straight line, it just gets blocked, and we don't care about it anymore, right? And so after these silver atoms came out, they came out of the slit. We now know that they're in a straight line or that they're collimated, right? They pass through this magnetic field created by these two magnets here, right? And so the important thing to remember about this magnetic field is that it's inhomogeneous, meaning that it's not constant throughout space, right? This is not a uniform magnetic field. Um, and so just keep that in mind for later, right? But what they found was that you send these silver atoms through this inhomogeneous magnetic field, and you see that when you have a detector screen at the end, that you only observe 2 points or 2 locations where the silver atoms are going to be hitting the detector, right? And so when you see that, you're sort of like, what the hell's happening, right? In order to answer that, we have to actually look at the silver atom itself, and particularly this electron alone on this ring here. Right, before I talk exactly about that, let's just look at the rest of the electrons on this silver atom, right? So a silver atom has 47 electrons total, right? So 47 electrons, and that's composed of 46 electrons on the like sort of on their contained within this spherically symmetric shell or electron cloud, right? Plus one lone electron, right? And this lone electron is the important part, right? So these 46 electrons that are in their own spherically symmetric electron cloud, they have angular momentum individually, right? Each electron has its own angular momentum. However, because this electron cloud is spherically symmetric, the net angular momentum of the 46 electrons is 0. It's just the null vector or 0 vector, right? However, we still have this lone electron, right? This lone electron, it's by itself. It has its own angular momentum that's not being, canceled out by angular momentum of other electrons, on the same shell as it, because it's the only one on its shell, right? And so what we're able to say is that this lone electron, because it has some angular momentum not being canceled out by the rest of the electrons in the silver atom, and coupled with the idea that the 46 electrons, the 46 other electrons in the silver atom have no angular momentum, we can say that this silver atom as a whole is going to have an angular momentum, and that angular momentum is going to be solely dependent on this lone electron. So this lone electron is supplying all of the angular momentum of this, or all of the net angular momentum of this silver atom, right? And so what we're able to say then is, importantly, that mu, or the magnetic moment of this atom, is going to be proportional to the spin of this electron, right? And so in reality, there's a proportionality factor, right? But it's not important exactly what that is, right? However, if you remember from electromagnetism, you might remember that the interaction energy of a something with a magnetic moment, or just magnetic moment itself with a magnetic field, is given by negative mu dot b, right? And so this is a potential energy, right? And this is really just equal to the work that it takes to, or the work done. So essentially, when you put when you put something with a magnetic moment in a magnetic field, it's going to experience a torque to align with the magnetic field, right? And so this negative mu dot b is just equal to the work done by the torque that's aligning this magnetic field, or aligning this magnetic dipole, rather, right? And so you might also remember that force is given by the gradient, or the negative gradient of U. We use the potential energy, right? And so if we plug in this negative mu dot b for U, and we take the gradient, we're going to get some expression, right? But in this problem, this is this in the Stern-Gerlach experiment, this was the z-axis, right? And so in regards to the splitting of these, the splitting of this beam of atoms, we really want to be looking at the force on the z-axis, right? And so if we take the gradient, we only look at the z component, we'll actually find that f sub z is simply equal to the or is equal to partial over partial z times, or not times, I mean of mu dot b, right? Which is a really, really cool result, right? But the question is, what is that equal to? If we just take the z component of the magnetic moment, we can pull that out, right? And then we find that it's really equal to, or maybe more approximated by, mu sub z partial b sub z over partial z. And you might remember that I mentioned earlier that it's very important that the magnetic field in the Stern-Gerlach experiment be inhomogeneous, right? And the reason for that is because, remember, inhomogeneous magnetic field, right? So the reason for that is because if this b sub z is constant, or it's uniform throughout space, then partial b sub z over, or partial z, is 0, right? Since partial over partial z of the magnetic field is 0, and then we have 0 force, right? So if we had a homogeneous magnetic field, you're just going to see these silver atoms just go straight and hit the center of the detector screen, which does nothing for us. We don't learn anything about the experiment from that. Who cares, right? So so we've determined that it's very important that the magnetic field be inhomogeneous. But the next thing to consider is sort of, given this expression for S sub z, or for f sub z, I mean, why do we see two distinct spots? So all these atoms are going to have the same mass, and we know that F equals ma, right? So if all these atoms have the same mass, and there's only two possible locations, and this movement of the atoms is happening over the same distance for every atom, there's only two possible values of acceleration that could be causing this motion, just from like basic, introductory mechanics, right? And so what that means is that there's only two possible two possible forces in the z direction. Right? How does that happen? Right? So partial b over partial z is going to be the same for every single atom, because although the magnetic field is not constant throughout space, each individual atom passing through experiences the same magnetic field at the same point as every other atom passing through, right? Which leaves only one option left, and that's that mu sub z can only have two possible values, right? So we can say that this mu sub z has only two values, right? Really interesting result, right? So essentially, this magnetic moment is quantized. There's only two possible values for the magnetic moment, right? And so eventually we were able to determine that, S sub z, or the spin, the z component of the spin is equal to plus or minus h bar over 2, right? And so this was sort of like the big result from the Stern-Gerlach experiment. And really quickly, before we move on to sequential Stern-Gerlach apparatuses, let's just think about what would happen classically, or like what we would expect classically, right? So classically, you might expect that you sort of have, an even distribution of silver atoms, right? And they fill in this even distribution on the back. Right, and the reason you would expect that is because you would assume that coming out of this furnace, that the sort of magnetic moment of each atom is just going to be continuous. Well, like each atom is going to have a set magnetic moment, right? You would think so, and then, but that magnetic moment could be between, some value negative mu to some value mu. Right. These are vectors, right? So normally you would expect that it could take any value between negative mu to mu. But, and so the important part of this is that if it did take any value from negative mu to mu, this f sub z would be equal to, it would be continuous, right? Like you could have an atom with a mu close to 0, and then it would just barely split off in either direction, depending on which side of 0 it was on, right? But again, just to stress it, I know I've stressed it a lot, but what we actually found was that the magnetic moment is quantized. There's only two possible values, right? But this was not the entire Stern-Gerlach experiment. So the actual, honestly, I would say equally important. You could argue that it was more important or less important, I guess, but it doesn't really matter, right? Arguably, just an equally important result was about the sequential Stern-Gerlach experiments. So the first sequential Stern-Gerlach experiment is simply chaining together two SG-Z hat apparatuses. And so these are the same as the one I just talked about, right? So the SG-Z hat just meaning that we're looking at the result as a split on the z-axis. And maybe it would make more sense to say that we're looking at the result where the magnetic field is pointing in the z direction. Obviously, it's still inhomogeneous, so it's not entirely, it has more than just a z-hat component, maybe, but regardless, whatever, it's fine. So the first result was just chaining together, or the first sequential Stern-Gerlach experiment was just chaining together two SC plus, or SG Z hat apparatuses. So in the first experiment, you essentially pass it through normally like we did before, but we take the SZ minus component, which is the downward component, right? So we take the component that goes down there, and we essentially just block it off, right? We say, I don't care about it, whatever. I'm just going to block it off. It doesn't exist anymore. And we only send through the SC plus, which again is just the half of the beam that goes to the top side of the detector screen, right? And we pass that through another SGZ, and as you would probably expect, we actually observe that there is no more S sub Z minus component. So you don't have the splitting anymore. You have all of these atoms, so let's say they're coming through out of this first machine, you find that they all just go to the top. They all end up on the top. Right? Cool. That's actually what we would expect, right? I wouldn't doubt it. Right? But now we get into the second sequential Stern-Gerlach experiment, and that was when we took this SGZ hat and we put it through just like in the first one, but we then take the SZ plus beam just like we did before, but this time we pass it into an SGX hat apparatus. And what we found there, or what Stern and Gerlach found there, rather, is that you actually do observe two separate beams again. We observe an SX minus beam and an SX plus beam. And just to explain if anyone's slightly confused, the SGX hat just means that the magnetic field is in the X hat direction. So if you rotate this 90 degrees maybe, or maybe that would be a Y, I'm not entirely sure, but essentially it's just a different orientation such that the magnetic field is in the X hat direction. Perfect. So what we found is that even though we got rid of this SZ minus, we actually observed that we got two beams. So essentially what that means is that when we measure in a different direction, or along a different axis, we still have a splitting of the magnetic moments. Right? This isn't even too crazy. Like, you might even possibly predict this. Like, okay, sure, that's fine. I believe that. But now we take the result from part B, and we essentially pass that into another SGZ hat, or we pass in only the SX plus. Right? So just like we did with the SZ minus beam on the first SGZ hat apparatus, we cut it off. We say, don't care. Get out of here. I don't care about you. And then we only send in this SX plus. However, though, what you would expect probably, like your intuition would probably say that, oh, the SZ minus is still going to be gone. But this was not the case. Stern-Gerlach actually saw that the SZ minus came back magically. We got rid of it earlier, and suddenly it came back. How the hell does that happen? I'm sure they were like, oh, what is happening, right? And so what they determined from this is that you can't know you can't know SZ and SX simultaneously, right? Because if you were to know SZ and SX simultaneously, then this last part wouldn't be true, because if you're going to say that you know SZ plus, or if you say you're going to know SZ and SX simultaneously, then you would say that at this point, I know that there is no SZ minus, because I know that there wasn't before, and I know that I can know them both simultaneously. And then you would find that there is no SZ minus beam here. But we find that there is an SZ minus beam, which means that we can't know them both simultaneously. So essentially, like, the overarching idea of this sequential Stern-Gerlach experiment is that the selection of the SX plus beam, right, by this SGX hat apparatus, destroys any and all previous info we knew about S sub Z, and essentially went back to being random again. Because I didn't talk about this earlier, but Stern-Gerlach found that there was an equal distribution of SZ plus and SC minus, right? And you will also find that in this case here. You have an equal distribution of SC plus and SC minus. So essentially, the main thing you need to understand is that the SGX hat just erased all of our previous info about S sub Z and allowed it to be as if we never measured S sub Z in the first place. And another thing that Sakurai notes in this section is just that quantum mechanical limitations are sort of inherent in all microscopic phenomena. So when you're dealing with like really small or microscopic things, quantum mechanics is going to show up a lot. It's going to be very prevalent. And the last section in Sakurai, section 1.1, is about an analogy of the results in the Stern-Gerlach experiment with the polarization of light, right? And so one thing to keep in mind is that when I'm talking about the polarization of light here, it's essentially purely classical. Of course, everything, quantum mechanics is part of everything, actually, right? But when you're dealing with like a ton of photons, as we are with, an actual full beam of light, then I'm going to be talking about it from a mostly classical lens. Right? And so, just as a refresher of how light polarization works, if you send some unpolarized light, meaning it doesn't have a specific polarization, through an X filter, you will find that this light is now X polarized light. And then when you send it through a Y filter, you get nothing, because X polarized light and a Y filter, the Y filter essentially is at a 90-degree angle with respect to the polarization with the X. Like the Y axis is at 90 degrees with respect to the X axis, right? So essentially, when you're sending X polarized light through a Y filter, you get nothing because none of the light can pass through. Maybe this diagram is better, right? So this horizontally polarized filter, or this X filter, you're sending this X polarized light through, and then essentially it's all, let's just say that it's all horizontal. Light isn't actually really horizontal or vertical, right? But essentially it just can't get through. It can't pass through a Y filter. However, if you first pass some unpolarized light through an X filter, right? Again, you get this X polarized light, and then you pass it through an X prime filter. Now you get X prime polarized light, right? And this light is actually at a 45-degree angle with the X axis and a 45-degree angle with the Y axis. So if we were to like draw it out, like this is the X axis, this is the Y axis, right? X prime polarized light is going to be at a 45-degree angle with respect to both of them. And essentially what that means is that the Y filter lets some of that light through. So it only lets through, I'm pretty sure half of it, as you might intuit or might guess, right? So essentially, it's not letting all of this X prime light through, but it's letting some of it through. And so what we can sort of, or how this is sort of an analogy to the Stern-Gerlach experiment, is that this X prime filter is sort of like the SG X filter, where if you sort of think of the X and Y filter as, or let me rephrase that. So essentially, just like with the Stern-Gerlach, we get some light out, right? We get something out of this first apparatus, and then we pass it to the second apparatus, and we see that we get something else, right? So we get more light. That's cool. And we pass it to the third apparatus, and you can sort of think of it as like sending it through SGZ again. This is where the analogy falls apart a little bit, right? But essentially, the main analogy is that originally, when we went straight from X to Y, we got no light. But now, when we go from X to X prime to Y, we now get light. And so that's the same as the Stern-Gerlach, where if we go from if we go from SGZ to SGZ again, we found that there was no SZ minus component, right? So the light, that's our light that's gone in this case. But when we send it through an SGX before the second SGZ, then we got the light back. And again, the light is going to be our SZ minus beam in this case. And so this is like it's really a cool analogy, or really, I think it's a really good analogy. I like the Sakurai uses it. The only thing you need to keep in mind is that this polarization of light is classical. It is not quantum. There is polarization of individual photons, which is quantum mechanical, but that is not what's happening in this case. We're talking about a collection of a lot of photons, right? And so Sakurai goes into talking about how we can sort of get into a little bit of broadcat notation and writing an overall state as the sum of the plus and minus states. And so he gives I'll write it down actually, but he talks about how this X prime polarized light can be given by this, or not KZ, KX, KZ, can be given by this function. right? And the main part, or the important thing to see in this function is that you have 1 over root 2 x hat, and you're also going to have 1 over root 2 y hat in it, right? So essentially, you have this addition of 2 different sort of states, right? 2 different sort of polarizations of light in this case, right? But where he connects this back to quantum mechanics is that we can sort of analogously say in the Stern-Gerlach experiment that if we have SX light, and he specifically specifies SX plus, right? This is equal to 1 over root 2 SZ plus 1 over root 2 SZ minus. Right, and this notation here is Brockhead notation. It's not super important. Essentially, Brockhead notation just defines defines vectors. So these vectors would be 1, 0 and 0, 1 respectively in the z hat basis or in the z basis, right? But essentially, just the important thing to recognize here is that we had this SX state, and we can actually say it's composed of these other 2 states. And so this is actually a superposition state. So it's not like these states are. It's not like there's half of an SX atom, or half of an atom that we found to have SX plus spin or angular momentum is going to be composed of half SZ plus and half SZ minus. It's actually a superposition, so we don't actually. It doesn't have a definite angular momentum. It's actually a superposition of these 2 angular momentums. And so Sakurai, he also goes on to talk about right circularly polarized light, which I don't remember which direction, like clockwise or counterclockwise, that goes in, but essentially that's like sort of spiraling light. Like maybe you'll sometimes see it like spiraling downwards on like the z-axis. That obviously wouldn't be like right circularly polarized light on like on the x-axis or anything, but essentially he talks about right circularly polarized light, and he gives an expression for it. I'm gonna write it down because it's sort of important, but it's not important exactly like what the equation is, but it is sort of important what the coefficients on the x hat and the y hat are, particularly the coefficient on the y hat, right? And so we have this expression for right circularly polarized light, epsilon. Or I don't remember if this is the entire function. I remember, I believe in Sakurai there's like some function of epsilon, but it doesn't matter. Essentially, all you need to understand is that there's this 1 over root 2 and this I over root 2. And we never talked about the y-axis Stern-Gerlach experiment. But we can say analogously from this, if we treat this right circularly polarized light as being analogous to like a y-axis Stern-Gerlach experiment or an SGY hat apparatus, we can then say that S sub y plus minus, because you can have SY plus or SY minus, right, is going to be equal to 1 over root 2 SZ plus or minus I over root 2 SZ minus. So this is very similar to the SX plus, like I'll put the plus minus here. So plus minus would be plus or minus, right? So the most important thing to see here is that we had this imaginary coefficient, and there's not much else to say about that. There's an imaginary coefficient, and that's honestly, to me, I find it very interesting that shows up. Just a quick aside, this is not actually related to quantum mechanics, but if you're ever working with polarized light, and you just want to understand a little better You should look up Jones calculus or Jones vectors. There's like a Wikipedia page for it. Just a really helpful. I found it very helpful for thinking about polarized light and doing linear algebra with polarized light states. Right, and then there's just like one last thing I wanted to reiterate. I mentioned this earlier, but that the polarization of an electromagnetic field, which is what we were talking about here, right? Polarization of light. When I was talking about light, I was talking about an EM field as a whole, is not the same thing as polarization of individual photons. So just make sure you don't mix those two up, because again, this is a classical observation that that like if you send something through an X filter and then a Y filter, you get no beam out. Right. That was kind of it. Did not go as that was my first video. Right. Did not go as well as I thought it might, but hopefully someone could learn something from that. I know it definitely helped me determine more about maybe what I understand and don't understand, and hopefully it's helped someone else with that too.